In this video, we're going to review the polar coordinate system from pre-calculus. We're going to use it later today. We will also be using polar coordinates several weeks from now when we talk about what's called the cylindrical coordinate system, which is an alternative coordinate system for three-dimensional space. To set the stage, when we first learned about the XY plane and how to make graphs in two-dimensional space in algebra, we describe locations in two-dimensional space using two numbers, right? One number x, one number y. And to locate points in two-dimensional space using these two coordinates, someone gives you a specific x value, for example, -4, a specific y value, +3, and to reach the location in question, you start at the origin, go 4 units in the negative y direction, 3 units straight up, and here's your point. Now, the polar coordinate system is an alternative way of describing locations in two-dimensional space. Instead of using the coordinates x and y to describe locations, it uses the coordinates called r and theta. To understand the meaning of r and theta, let's again go into the xy plane. And let's suppose, for example, that someone gave me a value of theta equals 60 degrees and r equals 5 units. To locate the corresponding point in two-dimensional space, I would start by drawing the angle theta in the standard way that we draw angles in mathematics. I would draw the angle theta counterclockwise from the positive x-axis. So the angle of theta equals 60 degrees is being measured out counterclockwise from the positive x-axis. I'm going to draw a line segment that makes this angle with the positive x-axis. I'm going to draw a line segment out here. And I'm going to draw this line segment so that it's 5 units long. 5 being the value of r that I'm given in these polar coordinates. The point that I reach by moving 5 units along the direction corresponding to this angle, this point right here is the location that's described by r equals 5 and theta equals 60 degrees. So in other words, the polar coordinate system describes locations in terms of the angle between that point and the x-axis. That's the meaning of theta. And the meaning of r is the point's distance from the origin. We use this angle and this distance to locate points instead of using a horizontal and a vertical coordinate system. Now, notice in this definition that because r is defined as a distance, the values of r are always going to be greater than or equal to 0. By contrast, theta can easily be either positive or negative. If someone gives you a negative value of theta, then we just draw those angles clockwise rather than counterclockwise. So if someone gave us, for example, r theta equals 7, -45 degrees, then on the xy plane, that location would look something like this. 45 degrees drawn clockwise from the positive x direction. Draw out a line segment 7 units long. This point down here in the fourth quadrant, reached by following those directions, is the location being described by these polar coordinates. You can use right triangle trigonometry to establish some conversion formulas between the Cartesian coordinate system and the polar coordinate system. I'm going to mark down a certain point in two-dimensional space, and I'm going to describe this point both in polar and in Cartesian. Now, if I think about this point in polar, it would be described in terms of its distance from the origin, r, and the angle theta that it makes with the positive x-axis. If I describe this point instead in terms of its x-coordinate and y-coordinate, this vertical distance would be the value of y, and this horizontal distance would be the value of x. So as you can see, by marking down the x and the y and the r and the theta for this point, we've ended up generating a right triangle within this picture. So we can use this right triangle and the formulas from right triangle trigonometry to establish some conversion formulas between these quantities. So for example, if I use Pythagorean theorem here, I can establish a formula that will produce r given x and y. If I know x and y and I want to find r, I can find r by taking the square root of x squared plus y squared. And that's just Pythagorean theorem applied to this right triangle. One leg of length x, one leg of length y, and a hypotenuse of length r. I can also use the SOHCAHTOA formulas to make some conclusions. For example, if I think about the SO of the SOHCAHTOA, the sine of this angle is equal to opposite over hypotenuse. If I rearrange that equation a little bit, I get that y is equal to the hypotenuse r times the sine of the angle theta. Similarly, if I use the ka in the SOHCAHTOA, then I can conclude that x is equal to the hypotenuse r times cosine of the angle theta. And if I use the toe in the SOHCAHTOA, I could conclude, for example, that tangent of the angle theta is equivalent to y over x, opposite over adjacent. Now, this final formula in green can be used to calculate the values of theta by applying inverse tangent to both sides. If I apply inverse tangent to both sides of this equation, I get the formula that theta is equal to inverse tangent of y over x. Now, you may have noticed that I've begun to set up a piecewise function here, a piecewise conditional function for theta. And that's because I need to remember that arctan is somewhat limited in the angles that it can actually produce. Arctan is only capable of producing angles in a certain range. Arctan can only produce angles on the right side of the xy plane, angles between negative pi over 2 and positive pi over 2. So this formula can only be used to find angles that exist here on the right half of the xy plane. This formula, in other words, can only be used in instances where your x-coordinate is positive, positive x-coordinate putting you on the right half of the xy plane. If you're in a situation where x is negative and you're dealing with a point on the left half of the xy plane, you need to give arctangent a little bit of assistance in order to produce the correct theta values. If you're dealing with a point that's outside of arctan's natural range, then you have to assist arctan by adding 180 degrees to its output to produce angles on the left half of the xy plane. So this is the formula that we would use if we're dealing with a point that has negative x's over here on the left side, outside of arctan's natural range. Let's practice using these formulas to convert points between the polar and Cartesian coordinate systems. For example, here in part 1, they've given me a polar point 5, pi over 2. So let's go ahead and take this location and express it in the Cartesian coordinate system instead. So I can use the formulas that x is equal to r cosine of theta and y is equal to r sine of theta to find the Cartesian coordinates here. Cosine of pi over 2 is equal to 0. Sine of pi over 2 is equal to 1. So the Cartesian expression of this location is 0, 5. Let's check and quickly see that this makes sense. If I'm given a value of theta equals pi over 2, that's 90 degrees measured counterclockwise from positive x. And then r would have me move 5 units along that direction. So it makes sense in the end that the point that I've calculated has 0 for x and 5 for y, because I can see that my point is up here on the positive y-axis. Similarly, if they gave me r equals 3 and theta equals 45 degrees, I can go ahead and calculate the Cartesian expression of this same point. The Cartesian expression would be x is equal to 3 cosine of negative 45 degrees. Y would be equal to 3 sine of negative 45 degrees. So this would be 3 over square root 2, and this would be negative 3 over square root 2 using the unit circle. Let's check see this makes sense. The theta being negative 45 degrees is going to be drawn clockwise down into quadrant number 4. I'm moving 3 units in that direction. So it makes sense that I've gotten this value of x and y here, where the x is positive, but the y is negative, because that makes sense for an angle in quadrant number 4, as we've drawn. Now, something to be cautious of, if you are using a calculator to find these values of x and y, you need to be careful to make sure that your calculator's mode matches the angle that you're given. So in the first problem, the theta that I am given is in radians. And the reason why I know that theta is in radians is because there's no degrees symbol. Any angle given without units is understood to be in radians. So if I'm doing this calculation on the calculator, I need to make sure that my calculator is in radians mode when I ask it to execute on this formula. So what I would do is I would go to my calculator, I would hit the mode button, and I would check to see what's going on in this third line. I can see, for example, at the moment that radian mode is highlighted. So this would be appropriate on a calculation involving theta equals pi over 2 radians. And if I go ahead and calculate 5 times cosine of, oh man, I haven't used this calculator in a long time, pi over 2, I get the same x that we found manually, 0. And if I do 5 times sine of pi over 2, here's the same y that we found manually, 5. But let me show you what happens if your calculator is in the wrong mode for the angle theta you're given. Supposing, for example, that you accidentally had your calculator in degrees mode as you were doing this calculation. Now if you go to calculate 5 cosine of pi over 2, you're going to get an answer of 4.998, which is a total mismatch to what it should be based on the unit circle. Likewise, if you do 5 times sine pi over 2, this is a totally incorrect y value compared to what it should be for this value of theta. Similarly, if I go down here to part 2, notice that this value of theta is in degrees. So if I'm doing this calculation using a calculator, my calculator should be in degrees mode. So if I do 3 times, for example, cosine of negative 45 degrees, I get that answer of 3 divided by the square root of 2 that we calculated manually earlier. However, if your theta is in degrees, but your calculator is in radians mode, then the x value I calculate gets all messed up because it's interpreting this as negative 45 radians, and so we end up with an x value that's off by almost half an entire unit. So do be careful about that. Make sure you're paying attention to the units of the angles that are given to you to make sure that your calculator is in the correct mode for that angle. Now let's practice converting points from Cartesian to polar. For example, xy equals 2 comma minus 2. What would the corresponding r and theta values be for this point? To answer this question, I can just go ahead and use the conversion formula. R equals the square root of, in this case, 2 squared plus minus 2 squared, which is giving me, after simplification, the square root of 8. You can leave it in that format. You can simplify if you want to, but square root of 8 is perfectly fine. Then theta, in this instance, I would use the formula arctan of y over x, and I would leave it like that because we have a positive x value, which means that this point is going to be on the right half of the xy plane. So this would produce a value of negative 45 degrees, thinking about this from the perspective of the unit circle. Again, you can use your calculator to answer this question, but you just need to keep in mind what mode your calculator is in at any given moment, so that when you report on your answer, you can make sure that you're giving appropriate units for your angle. So for example, if I check my mode, I am currently in radians mode. So if I evaluate inverse tangent of negative 2 over 2 in that mode, I would get an answer of, roughly speaking, negative 0.79. So if I got my answer from the calculator while it was in this mode, I would answer negative 0.79 without any units, because a radians is what's understood when no explicit units are given. Whereas by contrast, if my calculator is in degrees mode as I do this calculation, if I then run that calculation again, I get an answer of negative 45, so I need to understand this as negative 45 degrees and explicitly give the degrees symbol on my answer in order for it to be correct. Let's convert the point negative 1, 4 to the polar system. So calculating r the usual way, the square root of minus 1 squared plus 4 squared is equal to the square root of 17. And then theta, in this case, would equal the arctan of y4 over minus 1. But then I need to add 180 degrees or pi radians to this result because this x-coordinate is negative. So this point is on the left half of the xy plane, which is outside of arctan's natural range. Once again, if I'm approaching this in calculator, I need to be sensitive to my current calculator mode. If I have, for example, my calculator in degrees mode, then as I'm calculating this value of arctan divided by -1, I need to add 180 degrees to the result to be consistent in terms of my units. So that gives me an answer of 104 degrees for this value. If my calculator were in radians mode instead, then I would need to add pi radians to the result to get the correct answer. So if I change the mode to radian, and I go ahead and do arctan of 4 divided by -1, in this case, I'm going to be adding pi radians to get the correct answer, which is 1.8 radian, which I could report as 1.8 with no units attached. When you're doing these calculations, bear in mind that you can always throw down a quick sketch to make sure that your theta value makes sense for the point that you're working with. So for example, if I'm working with a point up here at -1, 4, then it makes sense that I've gotten a value of theta that's larger than 90 degrees, larger than pi half, but not as large as 180 degrees. This value of theta makes sense for this location. Likewise, this value of theta from the previous problem, -45 degrees, makes sense for the point that I was given, with a positive x value and a negative y value. This point is down here in the fourth quadrant, so getting a value of -45 degrees makes sense for that angle. Finally, let's go ahead and convert the point xy equals 0 minus 7 to the polar coordinate system. The r value is equal in this case to the square root of 0 squared plus -7 squared. So that would simplify just to +7. But what about the value of theta? If I think about the formulas for theta that are currently on the board, notice that none of them are suitable for a point that has an x coordinate of 0, right? If I use any of the formulas here on the board with a point that has x equals 0, all of them will produce a division by 0 error. So let's go ahead and think about this point just graphically. Let's go ahead and draw the point and find the value of theta manually from the picture. The point I'm working with in this problem has a y-coordinate of -7, so it's positioned down here on the negative y-axis. As a result, the angle needed to reach this location can, for example, be taken as 270 degrees. Or, if you prefer, you could do theta equals -90 degrees. That would just be the sort of clockwise way to reach that same location. Both of these are correct. Either one is fine. I might have a minor preference for 270, just because I like that it's positive. So this would be my value of theta, which I found manually from the drawing, because when x is equal to 0, neither of the formulas that we've presented can be used. Now, in certain two-dimensional settings, a two-dimensional vector might be described to you using an angle. The direction of the vector might be described using an angle. For example, here, I'm dealing with a two-dimensional force. I'm told it has a magnitude of 15 Newton, and it acts along a direction that makes an angle of 120 degrees with the positive x-axis. So the direction of this force vector is being described to me in terms of an angle, this angle of 120 degrees. Let's go ahead and find this vector, find the vector's components. And if we think about what would be involved in finding this vector's components, it very much is the same as some of the polar conversions that we did earlier in this lesson. The vector that I'm trying to find, the force vector, makes an angle of 120 degrees with the positive x-axis and has a magnitude of 15, so in other words, a length of 15,
And so essentially what I've been given is the value of r and the value of theta for this vector. If I want to find the x component, I can use the conversion formula from earlier, which said that the x was equal to the radial distance, in this case 15, times cosine of the angle theta, in this case 120 degrees. And the y component of my force vector will be y equals 15 sine of 120 degrees. So once again, either manually using a mental unit circle or using your calculator in the appropriate degrees mode, you can go ahead and evaluate this x and y component. The x component looks like it's going to be 15 over 2 negative. Visibly, I can see it's negative because we're over here in the second quadrant. And then the y value for 120 degrees, if I recall correctly, is 15 root 3 over 2. So this would be the component form of the force vector that has this magnitude and this angle. Another vector problem, someone gives us a inclined plane, a plane that's inclined 30 degrees below the horizontal. Now, to emphasize, we're not talking about an airplane here. We're talking about a plane in the sense of a flat surface. So to quickly sketch this situation, I have a horizontal line and I have a plane, I have a flat surface that is inclined 30 degrees below this horizontal. So my incline maybe looks a bit like this, where this yellow is a horizontal, this green is the inclined plane, and it is inclined 30 degrees below this horizontal. So then they ask me, find a unit vector parallel to the plane. Find a unit vector that points in the same direction as this plane. So if I draw the vector in, for example, here, they're asking me for a vector of length 1, because it's a unit vector, that points in the same direction as the plane. Once again, I can understand this problem through the perspective of a polar conversion. I'm given the magnitude, the length, the radial distance of this vector, 1 unit, because it's a unit vector. And I'm also given the vector's angle measured relative to this horizontal line, 30 degrees below. So I could find the x component of this vector just by using the formula, the radial distance, here 1, times cosine of the angle negative 30 degrees. Negative because we're below the horizontal, because this angle is being measured out clockwise. The y component, likewise, of this unit vector would be 1 times sine of negative 30 degrees, which means that the unit vector, that I might call u for short, u for unit, would be equal to what these two trig values produce. Root 3 over 2, positive, and sine of negative 30 degrees is minus 1/2. Okay, in this video we reviewed polar coordinates. The polar coordinate system was an alternative way of representing locations in two-dimensional space. Instead of representing locations using a horizontal x component and a vertical y component, we represented locations using a radial distance r and an angle theta, as measured from the positive x-axis. Using right triangle trigonometry, you can establish some formulas that allows you to convert back and forth between polar and Cartesian. For example, r is equal to the square root of x squared plus y squared, x is equal to r cosine of theta, y is equal to r sine of theta, and the formula for theta is piecewise. It depends upon whether your point is on the right half of the xy plane or if it's on the left half of the xy plane. If your point's on the right half of the xy plane, then the location of the point is consistent with the natural range of inverse tangent. So theta can be found via inverse tangent of y over x. However, if your point is on the left half of the xy plane, outside of arctan's natural range, you need to add 180 degrees or pi radians to the output of arctan in order to get the correct value for theta. Those formulas can also be used to find the x and y components of a vector if you're given the vector's magnitude and its angle measured relative to the positive x-axis. If you're given the vector's angle and you're given the vector's magnitude, you can find the x and y components using sine and cosine.